Good morning, everyone. My name is Chen. I'm a graduate student from Dr. Levy's group at the University of Pittsburgh. My topic today is broadband terahertz spectroscopy of two-dimensional nanoscale materials. As we know, two-dimensional materials, for example, graphene, molybdenum disulfide, and tungsten diselenide, have attracted intense research interest in the past decade. Their unique electronic and optical properties offer the promise of novel optoelectronic applications in terahertz regime. Today we'll discuss the initial efforts in terahertz spectroscopy of these 2D materials with a recently achieved broadband nanoscale terahertz spectrometer. This spectrometer is achieved on a material called lanthanum aluminate and strontium titanate. It has a lot of interesting properties. For example, a quasi two-dimensional electron liquid can be formed at the interface between LEO and STO. There is a critical thickness for LEO layers, about 4 unit cells, above which the interface is conducting, and for 3 unit cells, which is just below the critical thickness, a metal insulator phase transition can be introduced by applying different gate voltages. We can also create and erase nanoscale conducting regions at the interface with the method of conductive AFM lithography. This animation will demonstrate an example of the writing and erasing process. We apply positive voltage on the conductive AFM tip to write and a negative voltage to erase. So first, we apply positive voltage on the AFM tip and write two triangle-shaped patterns to help form a robust electric contact between the interface and the gold electrode. Then, also with a positive voltage, we'll scan the tip from one electrode to the other. When the tip reaches the second electrode, there is a sharp conductance increase, indicating the formation of a conducting channel. Then, if we apply a negative voltage on the AFM tip and scan the tip across the existing wire, we'll see a steep conductance decrease, indicating the formation of a junction. The mechanism behind the erasing and writing process involves localized modulation doping from surface protons. So this kind of nanostructures can be used to create nanoscale photodetectors at LLSTO interface. So here we apply a DC bias voltage on the source electrode and measure the photocurrent from the drain electrode. Light is focused onto the samples through an objective and can move around with a piezo stage. And here shows the scanning photocurrent microscopy measurement result. There is a strong photoresponse in the region of the nanojunction. Moreover, we can achieve broadband terahertz generation detection with this kind of nanostructures. So here is a 4-terminal structure. The width of the nanowires uncut are both around 10 nanometers. And this is the experimental setup. The ultrafast pulse coming from a tesaphier laser is split by a beam splitter. One beam goes through the optical delay line, and the other is reflected by the retroreflector. Then these two beams are combined by a second beam splitter and focused onto the junction. Again, we apply a DC bias voltage on the source electrode and ground the drain electrode. Then take the voltage difference between these two voltage sensing electrodes, delta V, as our signal. Here shows the photoconductance we measured as the function of time delay. The fall width at half maximum is about 31 femtosecond, which is consistent with the pulse width of our ultrafast pulse. And the fast Fourier transform shows a broad spectrum extending to 10 terahertz. So the mechanism behind this ultrafast response is believed to be the third-order nonlinear effect. So the nonlinear polarization is a product of the DC bias field across the junction, the third-order susceptibility at the junction, and two optical fields. And this unprecedentedly controlled terahertz radiation at 2 nanometer scales has been proved to be able to prove the response of a single plasmonic object. So here the nanoscale objects are commercial gold nanorods. From the extinction spectrum, we can clearly see there is a well-defined plasma resonance peak around 8-10 nanometers. So this is a longitudinal mode along the long axis of the nanorod. There is another peak here around 520 nanometers, which is the transverse mode along the perpendicular axis. After we deposit the gold nanorods onto the surface of our LOS2 sample, an AFM image is taken to locate ideal single nanorod. So here is a zoom-in AFM image showing this is one nice single nanorod. So after this is located, we'll design and create a phototerminal structure with a junction right underneath the single nanorod. Here shows the reflection and photovoltage scan. From the reflection scan, we can clearly see the position of the nanorods matches well with the AFM scan, and the photovoltage scan, which is delta V, the difference between V plus and V minus, as a function of laser spot position, shows there is one junction created at the interface. If we overlap these two images, now we can clearly see the junction is indeed underneath the single nanorod. And this is a polarization-dependent terahertz time domain signal and the corresponding power spectra. So when the light polarization is along the long axis of the single nanorod, both the terahertz signal and the spectral amplitude enhanced a lot. This is related to the plasmonic coupling with the induced terahertz radiation at the nanojunction. So now that we have this very powerful terahertz spectrometer, we can use it as a platform to study other nanoscale materials, for example, molybdenum disulfide and tungsten diselenide. The idea is to simply replacing the single gold nanorod with a CVD-grown single-layer molybdenum disulfide or tungsten diselenide nanoflake, and study its property using our terahertz spectrometer. Another thing we can do is to combine graphene with our device and study the graphene plasmonics. So our approach is to transfer CVD-grown graphene on top of LOS2 sample, then pattern it into an ideal shape. Write a phototerminal structure with a junction underneath graphene, and use our terahertz spectrometer to study the graphene plasmonics. We can also study its tunability by applying different gate voltages. So here is an AFM phase image of our sample after we transfer CVD-grown graphene and pattern it into a whole bar. The Raman spectrum shows a pronounced 2D peak with a sharp J peak embedded on STO mode. The single 2D peak with a higher intensity and very small D peak indicate this is high-quality single-layer graphene. We can also identify graphene using optical reflection scan. The zoom-in image shows large-scale and uniform graphene that has been patterned into a whole bar shape. So to prove graphene plasmonics, we first need to create a junction underneath graphene. So this is a phototerminal structure. Those are the four terminal leads. Again, we have source, drain, V plus, and V minus. The main channel is created in 3 steps. We first write the upper half of the curved wire, and then the lower half. There is a 10 nanometer gap between the ends of the 2 wires. And after finishing writing the second wire, we'll apply a negative voltage on the FM tip and touch down to create a junction. So this is a photovoltage scan. Again, it confirms that there is a nanojunction created at the interface underneath graphene. And this photovoltage can also be tuned by applying different gate voltages on the graphene. Here we focus light onto the junction and sweep the voltage on graphene from 0 volt to positive voltages, then to negative voltages and back to 0 volt. We also applied a square wave on the graphene and monitored the photovoltage simultaneously. And these are some preliminary results about probing graphene plasmonics using our terahertz spectrometer. From the terahertz time domain signal, the gray curve is from a clean LOS2 sample without graphene, and the colored ones are from a graphene LOS2 sample with different voltages on the graphene. So we can clearly see that there are additional oscillations from the graphene sample which have a frequency around 55 terahertz. Both plots here are normalized and shifted for clarity. So this is an ongoing project. We are still in the middle of studying the physics behind those oscillations. We think it's possible that those oscillations are from graphene plasmons, but there are also other possibilities. So in summary, we have developed a broadband terahertz spectroscopy using lanthanum aluminate and strontium titanate nanojunction. This technique has been proved to be able to prove the response of a single plasmonic nanorod. And we have also seen evidence for graphene plasmonic response up to 60 terahertz. This approach can be extended to study other 2D materials as well, for example, molybdenum disulfide and tungsten diselenide. So if you're interested in more LOS2 devices, the green ones are already given, but please come to the rest. And thank you very much for your attention.